to put all of this together, and we're going to take a look at how to graph rational functions using the 7 steps that we just defined. So for these last 2 examples, I would like us to sketch the rational function. And we'll take a look at the first one, and then we'll go on to the second one. The first one's going to be g of x equals 2x minus 1 divided by x plus 3. And we'll start off with that one, and then we'll define the second one. We need all the board space that we can get. All right, so I'm going to follow the 7 steps that we just talked about before, and the first thing we want to do is factor. And in regards to factoring, again, it's linear, so we're not going to worry about factoring. We really only factor if we have quadratic or above. Now, the next thing I want to do are find the x or y-intercepts. I'll start off with the y-intercept. And to find the y-intercept, we're going to let x equal 0. So I'm going to substitute in 0 every time I have an x. And it looks like 2 times 0 minus 1 is negative 1. 0 plus 3 is 3. So I have a y-intercept at negative 1/3. So the ordered pair 0, negative 1/3 is going to be on my graph. So what I'm going to do is I'm going to start putting together the information that we need on the graph right here. Okay, let's graph that ordered pair 0, negative 1/3. Well, right around here is negative 1/3 on the y-axis. So there's 1 point that's on our y-axis. Okay, so for the x-intercept, that's going to give us the zeros of the numerator. We get 0 equals 2x minus 1. Add 1 to each side, divide by 2. So we have an x-intercept at 1/2, which means the ordered pair 1/2, 0 is going to be on our graph as well. Let's graph that ordered pair. So here's 1. Oh, this is a convenient point. Here's 1/2. So here's 2 points that are on our graph already. Once we're done factoring, which is going to be factorable, finding the x and y intercepts, now I want to look for the asymptote. So let's start off with the vertical asymptote, also known as the VA. Now the vertical asymptote is the 0 of the denominator. So I'm going to go over here, take a look at my denominator, and I hope you see it's clear that negative 3 is our vertical asymptote. So we're going to say x equals negative 3. And again, we're going to represent that on our graph by using a dashed vertical line at negative 3. So there's our dashed vertical line at negative 3. And to find a horizontal asymptote, this is the one that's a little more complicated. We're going to use the degrees of the numerator and degrees of the denominator. Now our numerator is a first degree polynomial. Our denominator is a first degree polynomial as well. And remember, when the degrees are the same, we're just going to take the ratio of the leading coefficients. So what that means, I have a horizontal asymptote at y equals, well, I have a coefficient of 2 in front of my x term over here. That's our leading coefficient. There's a little hidden coefficient of 1 over here. So I have a horizontal asymptote at 2 over 1, which is the same thing as saying 2. I'm going to graph a horizontal line at 2. We're going to use that same dash notation that we used before. Okay, so we're putting together some information to help us figure out what the graph of this function g of x looks like. Keep in mind that our final result here will be a beautiful filled-in graph, and there's only going to be holes in our domain anytime we have a vertical asymptote. So that means all of our x values should be covered except wherever we have a vertical asymptote, which is over here at negative 3. And that's where the 6th part comes in. So let's talk about this 6th part. And part 6 says the following. What we want to do, remember our vertical asymptote represents an infinite wall. So we're going to approach the infinite wall from 2 directions. Now notice we have a vertical asymptote over here at negative 3. So that means I'm going to let my x values approach negative 3, which is over here, from 2 directions. I'm going to approach it from the right-hand side and then from the left-hand side. Negative 3. Now the way that we write that mathematically is we put a little minus in the upper right-hand corner. That doesn't mean negative. That just means negative 3 from the left. So what we're doing is we're trying to figure out what's happening in this direction of the graph as I approach negative 3 coming from the left-hand side. And again, I'm going to approach it from the right too, and we're going to write that as negative 3 plus. And that plus means I'm coming from the right-hand side. It doesn't mean positive side, it means the right-hand side. So we're going to approach the vertical asymptotes. In this case, I only have one, so I'm going to approach it in two different ways, one from the left and one from the right. Now, what we're going to do is we're going to choose a value that's very close to -3 on the left-hand side, and then choose a value that's very close to -3 on the right-hand side, and substitute that in for x. A number that's really close to -3 from the left, a little bit less than -3 is -3.1. A number that's a little, as we're approaching -3 from the right, a number that's a little bit to the right of -3, a little bit bigger than -3, is -2.9. We're going to use these numbers to help us to determine what's happening to our graph the closer we get to that vertical asymptote. So -3.1, here's what we're going to do. We're going to substitute it back into the original function that we had, which is right over here. And the only thing I want you to concern yourself with is our quotient going to be positive or negative? That's it. We don't care about exact values. You can find it if you want, but you don't have to. We're just concerning ourselves with, is our quotient negative or positive? So when we substitute -3.1 in, 2 times -3.1 is a negative, minus 1 makes it more negative. So in our numerator, we have a negative. -3.1 plus 3 is also a negative. And as you know, a negative divided by a negative is a positive. Here's what this is telling us. As our x values approach -3 from the left, our y values, or g of x, are approaching positive infinity because the quotient was positive. Let's try one more. Let's see what happens as our x values approach -3 from the right. Now again, the number we chose to represent this, and you want to stay pretty close to the vertical asymptotes and make sure your direction's correct. So a number that's a little bit bigger than -3 is -2.9. We're using that to represent the region of that value, and we're going to see if that's going to give us a positive or negative quotient. We're going to substitute that back into the original equation. 2 times -2.9 is negative, minus 1 is still negative, divided by -2.9 plus 3, which is positive, and negative divided by a positive is a negative. So this information is telling us a lot. Let's put this information together and help us finish graphing what this function looks like. So what we're going to do, because we have some points on the graph over here, we're going to put it together and keep in mind the following rules. We cannot cross over the vertical asymptotes. The whole domain of the graph should be covered. That means I should see a picture of a graph everywhere on here except where we have a vertical asymptote, and we're going to stay near the horizontal asymptote. We can cross over it, but we want to stay near it. So let's take a look at what each piece is telling us. As x approaches -3 from the left. Okay, so what I'm doing, I'm the graph over here. I'm getting closer and closer to -3. Here's -3 over here. As x approaches -3 from the left, my y values are going to approach positive infinity. So what that means, the closer I get to -3, my y values are going to go up to positive infinity. So we have a piece of the graph in terms of what it looks like. We're going to stay near the horizontal asymptote, and the closer I get, I'm going to shoot up to positive infinity. So I'm staying near the horizontal asymptote. As my x values get closer and closer to -3, my y values are approaching positive infinity. So that's what one part of the graph looks like. The second half of the graph, as x approaches -3 from the right, now I'm coming from the right-hand side. I have to stay near my horizontal asymptote, but now I have two ordered pairs I know that my graph has to go through. As x approaches -3 from the right, my y values are approaching negative infinity. So we're going to do this. We're getting closer and closer to -3 from the right-hand side. My y values, I have to go through these 2 points. I'm staying near the horizontal asymptote. I have to go through these 2 points, and my y values are going to approach negative infinity the closer I get to -3 coming from that direction. So this is a pretty good picture as to what the graph g of x equals 2x minus 1 divided by x plus 3 looks like. Now when you get to calculus, you'll be a little bit more specific in regards to what these pictures look like by taking derivatives, but for now, this is good enough. Let's do one more example, and we're going to use the same 7 steps. But this example is going to be a little more complicated. And let's take a look. So the same thing, I'm going to use the 7 steps to graph it. Let's take a look at the rational function. of x equals x minus 3 divided by x squared minus 3x minus 4. All right, so the first thing we're going to do is, in order for us to graph this, is to factor it completely. So the factored version of this looks like x minus 3 divided by x minus 4 times x plus 1. Right, two numbers whose product is negative 4 that sums to negative 3 are going to be negative 4 and positive 1. Now the next thing that we want to do, or we want to find any y-intercepts. And the y-intercepts are what happens when we substitute 0 in for x, and you can substitute it into either the factored or the unfactored. It's easier to do it in terms of the unfactored. And we get the following. We get the y-intercept, h of 0 equals 0 minus 3 divided by 0 squared minus 3 times 0 minus 4, which ends up giving us negative 3 over negative 4, or 3/4. So we have a y-intercept at 3/4. Let me graph a plane. Let me graph a Cartesian plane. We have a y-intercept at 3/4. So here's our y. Here's 1. 3/4 is a little bit below 1, so we'll put it right there. For x-intercept, 0 is of the numerator. Add 3 to both sides. We have an x-intercept at 3. So that's